So today we are going to discuss a new topic, that is your, let me just share it. Okay, is it visible?
Yes, sir. Yes, sir.
Okay,
Yes,
so
sir, visible.
okay, so today we are going to discuss about forces. Okay, what are the different types of forces are there, and we will discuss about what are the various supports are there, support constraints, and why they are important to our structures. So there what is force? Basically it is the action of one body to another body. That is the simplest way you can define force. It is the action of one body on another body. So the two bodies can impart action by making contact or without making contact also. Okay, so when the two bodies are making contact, they will impart reactions. Okay, and those forces are called as contact forces. Okay, and when the two bodies are able to react without having contact, so those basically will be called as non-contact forces. Okay, and in other terms we call them surface force or body force. Okay, so you can see over here that in this diagram, that if a body is there and we are going to apply a concentrated force over here at a certain point. Okay, so this particular force is in a certain direction. Okay, it will have a magnitude and a direction. Okay, so it will be a vector quantity. Hmm. Then we have this type of force. This is called, if this force is being distributed over a line or a length of a body. Okay, so that will be called as linear distributed load or a force. So it can be varying or it can be uniform. Okay, suppose a wall is being constructed over a slab or a floor. So the you can say that the weight of the wall is uniform throughout the length of the floor. Okay, so that way you can imagine that that would be a linear distributed load, and that load is basically will be given by Newton per meter or kilonewton per meter. Okay, or Newton per mm. So that will be the unit, and a unit of force would be, concentrated force would be only Newton or kilonewton. Okay, then we have this type of force. This is basically surface force. It is being, when a force is being applied over an entire area of a body, so that would be called as surface force, or we call it as pressure. Okay, area pressure or flow pressure, different terminologies are there. So the unit of this force will be how much? Surface force?
1 Newton meter.
No, it will be
Newton per meter square.
Newton per meter square. Okay, means at per meter square of area, what will be the load that would be applying over there? Okay, so that would be Newton per meter square area. That would be the unit of pressure basically. Okay, then we have body forces. So body forces are non-contact forces, and like gravitational force is there, or force due to gravity that would be acting at CG of this body over here in terms of weight. Okay, so that would be a body force. And you can say magnetic forces, electrostatic forces, that those are basically non-contact forces. Okay, the two bodies need not to contact with, in physical contact with each other. Okay, then we have different constraints on the body. Okay, so why do we need constraints in a body? Suppose let me just on this camera over here. Okay, is this visible? This box is visible.
Yes, sir.
Okay,
Yes,
so
sir. Yes,
if
sir.
if I am applying a force, suppose this box is suspended in a space, and if I am applying a force over here, okay, then what will happen? it will displace it will displace from the
direction of force.
okay, it will go into the direction of force. Okay, but our main aim is the purpose of this box to stand still. Okay, so that would be in static equilibrium. Okay, and we need a constraint on this end or any other end so that this body should not move with the application of this force. Okay, so we have different types of constraints. What are those types? Basically, roller constraint, pin constraints, sliding constraint, and fixed constraint, and basically we call it as the supports also. Okay, so you can see in this figure over here that what is roller support. So suppose end of the body is being uh, acting as a roller, means what is happening over here means that if this end is roller, then this end of the body is constrained in moving in vertical direction, but it is allowing itself in horizontal direction. Okay, so there are two types of constraints, translational and rotational. Okay, so if a body is constrained in rotation, then what will happen? It will not rotate. And if the body is constrained in translation movement, then it will not translate with the action of or application of any force. Okay, so we have different and due to these constraints, what will happen due to the application of force on a body, these support will transfer reactions on the wherever they are supporting. Okay, suppose this figure is there, this is the bridge, and this is the roller support that they are providing over here over the pier. Okay, so whatever the force that is coming onto the bridge, it is being supported, transferred into this beam. Okay, and then the force is being transferred into this support with the help of roller support over here, and then it is going into the pier. Okay, but what is happening over here, the only vertical force will get transferred. Okay, not the horizontal force. Why? Because this constraint is not providing constraint to horizontal movement. Okay, so when a force is applied on this bridge in horizontal direction, then what will happen? It will move slightly in this direction. Okay, so the roller support will always provide constraint in vertical axis. Okay, it will not move the body in vertical axis over here. You can see over here, and one reaction will be provided due to the roller support. Okay, so the load is going to transfer in vertical direction, and what will be the vertical direction means what will be the transferred load, that will be the reaction that would be applied due to the support. Okay, so also you can see if your surface, if your roller support is like this, then it is able to move in vertical direction, but it cannot move in horizontal direction. Okay, so it depends upon how you are aligning or how your support is working. Okay, in the machine or in a structure. Okay, so see this is the vertical roller constraint, means it is basically it cannot go in this horizontal direction, but it can slide in vertical direction. Okay, so these are the vertical rollers, and this is basically in two dimensions you are seeing. If we can see in we can analyze this our body in three dimensions, then what will happen? uh, you can see over here, it's this support can move in x direction and z direction, but it cannot move in y direction. Okay, so this is how the roller support works. Okay, so different types of different supports are there, so they provide you constraints in different directions, in translational as well as in rotational. Okay, so you can see over here this pin support over here. Okay, so it allows, yes.
Sir, this roller support for the bridge, it is fixed the between the beam and the
No, it is
beam
not fixed. It is not fixed. It's just
Okay.
basically resting there with the help of assembly. Okay, so it won't go over the pier. Okay, and
Sir,
there.
during So during earthquake, when there is motion from all the
Yeah,
sides, what
yeah,
happens
there
that
will
time?
be the motion. So what they do, they provide a certain limit so that it can move around, but it will not go further that limit.
Okay.
Okay,
Okay.
so in you can see in flyovers also they provide bearings under the this girders. Okay, so these are basically longitudinal girders. Okay, and under these girders they provide bearings. Okay, so why the bearings are being provided over there? To cancel out the vibrations of the bridge. Okay, so when vehicle
Okay.
moves over the bridge vibrates. Okay, so we do not want those vibrations to transfer into the piers. So what will happen if those vibrations get transferred into the pier? Then it will cause cracking and basically failure of the pier over there. Okay, so that's why we provide bearings in the bridges.
Okay, sir.
Hmm. So this is the pin support you can see in you have seen in various truss mechanisms in trusses and roof trusses and also in bridge trusses. Okay, so you can see over here how this support works. It allows the movement of body in rotation, but it won't allow the movement of body in translation. Okay, so it cannot move, the body cannot move in horizontal as well as in vertical directions, but it can rotate. Okay, so two constraints will be there in horizontal as well as in vertical direction. So whatever the load is coming onto the body, it will get transferred into this surface or this different body. Okay, in which this member is being attached over here. So it will transfer into translation reactions over here. Okay, so you can see in this this is basically supported on a vertical wall. Okay, like this, and this is the basically you can see over here, this is the pin support in 3 dimensions. So it will transfer the incoming load onto the member in three constraints. Okay, three constraint reactions: translation reaction Rx, Ry, and Rz. Okay, it won't allow it to translate in x axis, y axis, and z axis, but it can rotate. Okay, this is the sliding support, and you can see in different mechanisms over there. So what it does basically, it allows your member to translate in one direction, but it cannot allow it won't allow the member in translate in this direction, and it won't allow it to rotate also. Okay, so you can see this problem over here, this example of a gantry crane. Okay, so what happens, this support mechanism, what is going on there, when you switch on the remote, it will move in this horizontal direction, it won't move in vertical direction. Okay, and it won't also rotate. So there are two constraint reactions over there, one translation reaction and one moment reaction. Okay, or rotation reaction you can see over here. And this last support is called as fixed support, and this is basically fixed into a wall. Some member is fixed into a wall, so neither it can translate. Okay, so it won't allow it to translate or it won't allow it to rotate also. Okay, so fixed condition you can see in your homes also, like a pole you can see. So the end of the pole, one end of the pole is free and one end of the pole is fixed into the ground, so it won't rotate and it won't translate also. Okay, so how many reactions it will produce over here at the support? So it will give you two support reactions in two translation reactions and one movement reaction. Okay. Okay, so one moment reaction will be there in 2 dimensions, and if you are seeing and analyzing your structure in 3 dimensions, so how many support reactions will be there? Three translation reactions and three moment reactions will be there about each axis. Okay, x, y, z. So why these support reactions means is are important. So basically, yes.
So if there is a fixed beam, then how many total reactions will be there?
Yeah, we will discuss about that. Okay, at one end there will be, if you are analyzing it in two dimension, yeah, or you can, yeah, there will be three support reactions. Okay, if you are analyzing in three dimensions, then there will be six support reactions at one end. Okay, three translation and three moment reactions.
Okay.
So we will, when we will analyze those things, so then it will become more clear to you how will we see, analyze those things also, and how will you imagine and assume those support reactions over there. Okay, so why these supports are important? These supports provide constraints to our body, so that our body should be in equilibrium, either dynamic or static. Okay, so and also whatever the reactions they will impart to another body, you have to calculate it, you have to analyze it, so that you can calculate the amount of total amount of forces that are generating inside these members. Okay, so that's why it is important to visualize and see how the reactions are working over there, and what are the transferred load, that is basically the value of these reactions would be there. Okay, so that basically comes into the analysis part. And for statics, what we use is, we use equations of equilibrium for analyzing these unknowns basically. So these are unknowns. So we have different types of loadings. Four types of loadings are there basically. So we have two types of forces, and we have two types of moments. Okay, so we have normal force that would be acting perpendicular to the cross section area, or acting along the longitudinal axis of the body. Okay, and there will be a shear force that would be acting across the cross section of the area, like or transfer force you can see over here. Okay, and it will be acting in across the cross section of the body. I will show you the diagrams also. Then bending moment, what it does is, if you apply a moment due to it is coming onto a body due to a force or a couple. Okay, if a moment is being applied on a body, then what is happening over here, it will try to twist or bend the body. Okay, so it is based upon the application of the moment, how the moment is being applied on a body, so it will deform the body in that way. Okay, so these are the basically equilibrium equations that we use to analyze the unknowns. And what are the unknowns basically? We have support reactions, and we have internal forces and movements that would be developing inside the body due to the application of external loads. Okay, so we use equilibrium equations, and these are the equations for equilibrium. What are these basically? When a body is at rest, then to maintain equilibrium, all the forces that are acting on a body should nullify each other, so that the summation of the body in x, y, and z, if you can see over here, would be 0. Okay, so that our body should remain in equilibrium. Suppose if a force is acting on in this direction, if force is acting in this direction, force is acting in this direction. Okay, so if a body is to be at rest, so these forces must be equal and opposite, and also you can see the summation of all the forces should be 0, so that body should be at rest. And the moments that would be applied at the CG due to these forces means, when if this become unbalanced, what will happen, it will start to rotate. Okay, so the moments also should balance each other, so that our body should not rotate also, so it won't translate and it won't rotate. So that is the you can say situation, or the condition of body is at rest. Okay, So it should not rotate also, and it should not translate also, and it should not rotate also. Okay, so all the forces that are coming onto the body and all the moments that are acting about the CG of the body should be zero. Okay, so how to calculate these equations we will see in oncoming problems. Also we will take different examples. Okay, and what are basically, yes, मोमेंट का भी बताएंगे आपको, मतलब ठीक है. आई विल शो यू द डायग्राम्स, देन यू विल अंडरस्टैंड मोर क्लियरली. ओके, what are determinate and indeterminate structures? Okay, so determinate structures are those structures which are analyzed, which can be analyzed by using these set of equations. Okay, so these are basically fx is equal to 0, sigma fy is equal to 0, and sigma mo is equal to 0. These are three equations that are used for a body if forces are acting in one plane only. Means if you are analyzing a body in two dimensions, okay, in one plane, then these three equations would be you can say feasible to calculate all the unknowns. And if you are analyzing a body in three dimensions, then these six set of equations you have to analyze to calculate the unknowns. Okay, so if unknowns are more than these equations, then your structure will become indeterminate structure, and you cannot analyze by using these set of equation only, and we use other equations also like compatibility equations and energy methods to calculate indeterminate structures. Okay, so in this course we will analyze and we will study only determinate structures, and we use these set of equations only. Okay, so let me just open at this. Okay, so is it visible?
Yes, sir.
Okay, so as I've told you earlier, how many types of forces are there? So there will be axial force or normal force, and it acts along, suppose this is our body. Okay, so we have longitudinal axis and we have transverse axis. Okay, so you can see over here when the force is acting along the longitudinal axis of a body, it will be called as normal force or axial force. Okay, and if the force is acting perpendicular or along the axis of the transverse axis, so it will be called as tangential transverse or shear force. Okay, so it acts along the longitudinal axis of the member and perpendicular to the cross section of the body. Okay, so cross section will be b into h. Okay, and length will be this. So if normal force will always apply perpendicular to the cross section and along the longitudinal axis of the body. Okay, clear? What it does, how it will deform? It will deform, either it can create elongation or contraction in a body in form of this. Like if a force is if your force is acting like a pull on a body, so it will create tension in the body, and if a force is acting inwards, then it will create compression in a body. Okay, so tension will lead to elongation and compression will lead to contraction of the body. Okay, then what tangential force does? Tangential force basically it is responsible for the change in shape of the body. Okay, and normal forces are responsible for change in volume of the body. So it can elongate and it can contract, and these tangential forces are acting across the cross section of the body. Okay, and it will try to distort the shape of the body. Okay, so these are basically the shear force that would be responsible for that. Okay, angular distortion. We will see how to calculate these internal forces. So these are basically forces that will be generating inside the body due to oncoming load onto it. Okay, so there would be a normal force, so there would be a shear force that would be acting inside the body. Okay, then movements, whatever the forces that are acting on the body, external forces, those forces can create movement, or can act as a movement, as a bending moment also, and as a twisting moment also. Okay, so if moment is acting about the transverse axis, means about y or z. Okay, like this, y or z. So what it does, it creates bending in the body. And how it will bend the body, like in sagging mode or hogging mode. Okay, so it will depend how the movement is working, application of the movement. So if a body is being subjected to a movement like this, so it will sag, it will called be as sagging, means the concavity upwards and convexity downwards. And if a movement is being in opposite direction, applied in opposite direction, then the bending of the body will be in this shape, that is called as basically as hogging. Okay, and the moment associated with it, we call it as sagging movement or hogging movement. Okay, so it basically based upon the application of the movement. Okay, and if you apply the same movement about the longitudinal axis of the body, then what will happen, it will twist the body. Okay, so the same moment is being applied about transverse axes y and z, it will create bending in the body. When a moment is being applied about the longitudinal axis of the body, it will create twisting in the body. Okay, so is it clear?
Yes, sir. Yes, sir.
Okay, so twisting the body, basically we use this is a torque, we call it as, when the moment is applied about the longitudinal axis, it is called as torque or twisting moment. Okay, and when the moment is being applied about the transverse axis and it is creating bending in the body, so it is called as bending moment. Okay, and also in general terms, somebody has asked what is the definition of the moment. Definition of the moment, basically it is defined as the product of a lever arm into a physical quantity, and that physical quantity can be force, can be area, can be volume, or any other physical quantity. So that would be the moment of that physical quantity. Okay, so you might have heard term moment of area. hmm?
Yes, sir.
Second moment of area.
Yes, sir.
Second moment of area is basically commonly known as moment of inertia. Okay, and in physics, moment of inertia is basically mass moment of inertia. Okay, so that would be mr square. Okay,
Yes,
so
sir.
mass moment of inertia is different, second moment of area is different. Second moment of area is a geometrical property of a section, and mass moment of inertia is, you can say, the natural property, or you can say the yes, natural property of the material. Okay, so because mass is also associated with it, and it will define, you can say over here, the homogeneity of the material, how the homogeneous material is, and the inertial properties of the material. Okay, so second moment of inertia, we call it as, in general term, in books also you will see the second moment of inertia to be called as only moment of inertia, so don't get confused with that. Okay, the second moment of inertia is basically, for rectangular cross section, is bd cube by 12. And how it will come to it, we will see that later also, how will you calculate second moment of inertia and first moment, oh sorry, first moment of area and second moment of area. So in engineering mechanics also you will get to know this, there will be some topic that will be related to first moment of area and second moment of area. Okay, so there you can relate these things also. So you can see over here, means how the external forces and external moments that will lead into the development of internal forces and movement. Okay, and why do we need to calculate these internal forces and movement? Because we want to calculate what is the amount of force that is going to generate at a particular point in the body. Okay, and why do we need that? We need to calculate what is the maximum amount of force that is going there, that will be developing inside that body due to the oncoming forces. Okay, so that you can calculate the strength of that material or body or any structure. Okay, जब maximum limit उसकी पता होगी तभी तो आप कहेंगे कि ये इसकी strength इतनी है. Okay, so this is why the analysis of the structure is being done, and we will calculate the maximum amount of either normal force or shear force and moment. Okay, and these forces and moments will lead to development of stresses. Okay, deformation and basically stresses and strain. So we will talk about that later also, and basically the yielding capacity, or you can say the strength of the material, is defined in terms of stress. Okay, and by calculating that maximum stress that it can take, the body can take, that would be its strength. Okay, so that is the main purpose of analyzing the whole body and to calculate forces and movements and stresses, so that we can calculate what is the maximum amount of stress that it can withstand. Okay, so that is the basically whole structural analysis, why we are doing it. So you can see over here this body is there, and some forces are acting on it. And so if you want to calculate internal forces inside the body, means at any particular point or any particular cross section. Okay, so if you want to calculate what is the amount of forces or movements that are acting on that particular cross section, so how will you calculate that? Okay, so what we do is we assume that there are some certain forces and movements are actually developing over there. Okay, first of all you have to assume to calculate the variables. Okay, so these are the basically nothing but the unknown terms that we define. So what we assume is that at this particular cross section a normal force is acting, a shear force is acting, and a moment is acting, bending moment or a torque. Okay, so I have not shown the torque over here, but two forces and two moments that we assume always. Okay, and how do we assume that? We assume that the action of normal force is tensile. Okay, means you can see over here what is the action over here, means when the body is in tension, the force would be applied over here in outward direction. Okay, so for the sake of our calculation, and for calculating the actual nature of the force that would be applying over there, you have to assume first. Okay, so either it can be tension, it can the force can be tensile developing there, can be tensile, or it can be compressor. Okay, so first of all you have to assume one thing. So you can assume either the force is acting there is tensile or compressive, and after that after the analysis we can say that if it is our assumption was correct or wrong. Okay, so how do we do that? We will see. So first of all what we do is we assume that this normal force is acting outward, and the nature of this force is tensile. Okay, and the moment and the shear force is acting downwards. Okay, so why we take it as downward, I will tell you later. Okay, then when we'll go for a problem over there, so why it is downward. So you can take for upwards also, it's up to you. So we are taking this shear force positive downwards, and the moment that is acting over here is a sagging moment. Okay, and this is the same section that would be, this is here. So on this part the forces would be acting in opposite direction, so that you can see over here when these two sides will join together, so the action of these internal forces will nullify each other. Okay, so this is the left hand side and this is the right hand segment, this is the left hand segment, this is the right hand segment of the section. Okay, so what is the whatever the action of the forces that would be developing on this particular segment, the opposite action would be developing on this segment, right hand segment, so that they can nullify each other and our body should be in equilibrium. Okay, and this particular the method that we have done over here, the you can see over here the development of internal forces over here, this is basically called as free body diagram. Okay, so free body diagram of left hand segment and free body diagram of right hand segment. So we have shown over here what are the various external forces that are acting on the body and what are the various internal forces that are acting on the body. Okay, after that what we do, once we have shown the or reduced the free body diagram, we will go for analysis part. Okay, and how do we do analysis? We will use equations of equilibrium. Okay, so for 2D structure means suppose these two forces are acting in a plane, means there won't be any force that is acting in z direction perpendicular to the screen. Okay, so you can use three sets of equation to solve this problem. Okay, so two sets of equation will be of force, means summation of forces in horizontal and vertical direction. Okay, and summation of moment about this point, CG point. We have cut this point from the CG or any other point if you want to calculate it. So the moment that would be acting at this particular point. Okay, so summation of moment due to all the forces and the internal moment, that should be 0. Okay, so once we have means reduce those equations, so you can easily calculate the value of unknowns from there. Okay, so let's take this example over here. So a bar is there, suppose a mild steel bar is there. Okay, and it is being subjected to a tensile force at the bottom, and this end is pinned over here. Okay, so how many support reaction a pin support will provide? There will be two support reactions, Rx and Ry. Okay, so suppose you can imagine this problem to be a an example of a fan rod. Okay, ceiling fan would is there in everybody's home. Hmm? So a weight of the fan is being F, whatever the weight of the fan is, and this particular rod is there of mild steel, and this is basically pinned in the ceiling. Okay, so are you seeing that? Are you understanding it? Is there any problem? Hmm? Just you can see to the your ceiling fan and see how the things are working over here.
Yes, sir, understood.
Yeah, okay. So you can see over here that so we have created this problem in 2 dimensions. If it is in 3 dimensions, there would be 3 support reactions over here: Rx, Ry, and Rz. Okay, so there would be one force, vertical downward force, is acting at this particular end. Okay, so what is the amount of force that would be developing inside this rod? This is what we are going to calculate. Okay, so what we do is we just break this whole rod in 2 segments like we have done for this body. Okay, and we want to calculate what is the amount of internal force that is acting inside this rod. Okay, so it can be tensile or it can be compressive. Hmm? So how will you know for sure? So what is the amount of what is the type of force that would be developing inside the rod? Can you guess?
Internal force.
Internal force. Whether
So
it will be
tensile force.
tensile force or compressive force.
So tensile.
Okay, so if you are stretching a body, so what is happening? The rod is stretching due to this force, and there would be tension in the rod. So the force that is developing
Sir?
inside the rod would be tensile. Yes.
So can we analyze this question by
Principle of superposition.
Yes, sir.
We can, but we need to have number of forces for that. Okay, so we will go later for the principle of superposition. We will discuss that also.
Okay, sir.
Okay, so that is what it is basically. So what I am just coming from the beginning. Okay, principle of superposition is a bit advanced for this. Okay, so we use equilibrium equation, and what are those equilibrium equations? Sigma fx is equal to 0 and sigma fy is equal to 0 and sigma moment. Okay, so moment about which point? Moment about this cross section or this line, or you can see over here. So we don't need that because there is no moment is acting over here. So we have only vertical force overacting over here. So if we apply, we assume that a normal force of tensile nature is acting at this particular cross section over here, okay, of n. So what we do, we will apply equilibrium equation on this free body diagram, okay, on the lower half, and what it does basically, summation of Fy is equal to 0. If we see all the sum means all the forces should nullify each other, means summation of all the forces in vertical direction should be 0. So what are the forces that are acting over here? F and N. Two forces are there only.
Yes, sir. Yes, sir.
Okay, so this will be N. N is in positive y direction. Okay, and minus F. F in negative y direction is equal to 0. Okay, so what we are getting from here is that N is equal to F. So what is the amount of internal force that is acting inside the body is equal to F, and what is the nature of the force is tension. Okay, and you can see over here this is coming a positive value. Okay, and if it is coming a negative value, then what would have been there? Means it would mean that our assumption was wrong, and what happened, the internal force would be of compressive nature. Suppose if I flip this direction of the force, then what would happen? What will be the value of n by applying same equation?
So negative.
Yes,
Negative
so
n.
that would be
Compressive nature हो जाएगा.
yes, that would be n plus F is equal to 0, because this force would also be in positive y direction. Okay, so n plus F is equal to 0, so n should be in negative. Okay, so that way what we do is we first assume that our force, whatever the force you are calculating, we assume that the normal force is in tensile action. Okay, tensile nature, and it is acting outward from the cross section. If it is coming positive, then it is okay. Okay, our assumption is correct. If it is coming negative, then our assumption is wrong, and the nature of the force is opposite. Okay, so this is how we signify, or you can say we can determine the nature of the force. Okay, and also you are getting the value of the force, also magnitude you are getting, you are also getting the nature of the force, or you can say direction of the force, by seeing whether the value is coming positive or negative. Okay, and also what is the amount of reactions that are going to be transferred into the ceiling, that also you can calculate by applying equilibrium equation on this upper half of the uh, you can see over here, upper half of the free body diagram, or you can directly apply on the whole body also. Okay, so that would be it. So Ry would be equal to F. Okay, whatever the direction weight of the fan would be, and the horizontal force, there would be no horizontal force due to the uh, because there is no horizontal force acting, external force is acting, so there would be no support reaction in horizontal direction would be acting over there. Only one Ry will be there, and it will be transferring the load of the fan into the ceiling. Okay, so this is how we apply equilibrium equations and we calculate internal forces. Okay, so I think the time is up, and Yeah, we'll discuss other problems in next
सर
one.
एक्सक्यूज मी सर
Hmm?
सर इस वाले जो ये थियरीज में कैसे पता चला कि मूवमेंट जीरो है?
Because there is no movement is acting. If you are calculating moment about this support, what is happening? What is the action of this support? Is it allowing rotation or not?
यस सर, ये चेंज सपोर्ट सर
अगर हम इस एंड पे एक हॉरिजॉन्टल डायरेक्शन में फोर्स लगाएं तो क्या होगा बताइए?
ये रोटेट करने लगेगा।
रोटेट करने लगेगा। सो जब रोटेट करने लगेगा तो उस पर मोमेंट अप्लाई नहीं होगा। ओके, ठीक है ना? इट इज़ अलाउइंग इट दिस बॉडी टू रोटेट। तो आपने फोर्स लगाया, वो रोटेट कर रहा है कर रहा है कर रहा है। सो देयर वोंट बी एनी मोमेंट दैट वुड बी डेवलपिंग इनसाइड। मोमेंट कब डेवलप होगा? व्हेन दिस रोटेशन, व्हेन यू कंस्ट्रेन दिस रोटेशन ऑल्सो। ठीक है ना भाई? किसी बॉडी में इंटरनल फोर्स, इंटरनल रिएक्शन तभी डेवलप होगा ना जब आप उस चीज़ को कंस्ट्रेन कर देंगे। ठीक है? इफ़ यू आर अलाउइंग इट टू रोटेट देन इट विल रोटेट, इट विल रोटेट। ठीक है? अगर मैं इस सपोर्ट को फिक्स कर दूं, ये वाला जो सपोर्ट है, देन मूवमेंट विल कम इनटू पिक्चर। ठीक है ना? तो वो भी आएगा, कैसे मूवमेंट कैलकुलेट करते हैं, विल सी दैट आल्सो। ओके, so this slide is also available on your classroom. Just go and see, and we'll meet on the next term. Okay, and go through some problems in your tutorial sheet. We will discuss that also. So just go through it. What are those things out there? And you must go through a book, that is your R.C. Hibbeler, Mechanics of Materials by R.C. Hibbeler. So they have explained in excellent way, and when you go from the beginning, you will understand everything. Okay. So thank you for joining.